Hi, and welcome to section 11.5. In this section we're going to learn about quadratic functions and their graphs. So you know what a quadratic equation is. A quadratic equation is where you have a quadratic on one side and it says equals 0 on the other side. A quadratic function is instead of having it equal to 0, you have it equal to f of x. So it's of the form f of x equals ax squared plus bx plus c. That's a quadratic function there. Now notice it's not equal to 0. It's defined by this function, f of x. Okay, when you graph them and you plot points, you get something of this shape. Now that shape is called a parabola. All quadratic functions have the shape of a parabola. Okay, and I should mention up here, a, b, and c are just constants. They're just numbers. Okay, there's a little bit of terminology you should know. The vertex is this point right here. It's either at the very bottom or at the very top of the parabola. And the axis of symmetry, which is also sometimes called the line of symmetry, is that line that goes through the vertex. It's always a vertical line. And the vertex, the parabola mirrors itself over that line. As you can see, it acts like a mirror, but from here to here, from here to here, all the points mirror each other over that axis of symmetry. Okay, so what we're going to do in this section is graph lots of parabolas, and then we're going to get a hang of how to graph generally without having to plot points. So let's start with this example. We're going to graph three functions. Let's start with f of x equals x squared. I recommend that you do this by plotting points so that you'll really truly understand how I'm getting these points. Okay, if you plug into x squared, you'll get 0, 0. If you plug in 1, you get 1. If you plug in negative 1, you get 1. If you plug in 2, 2 squared is 4. Negative 2 all squared is also 4. 3 squared is 9. And so is negative 3 squared. And that's all that's going to fit on this particular graph. Now they do have a very curved shape at the bottom. It's not a sharp point there. It is curved. Okay, there's f of x equals x squared. Now that's the most basic quadratic function that there is. Okay, its vertex is at the origin, 0, 0. It opens upward. And its axis of symmetry, which is actually not something we refer to all that often, but its axis of symmetry is the y-axis right here. Okay, now let's graph the other two. We'll do those in different colors. I'm going to graph g of x in orange. Now g of x is equal to x squared minus 1. So let's do this by plotting points. Okay, if we plug in 0 into g of x, we'll get 0 squared minus 1, so negative 1. Okay, next let's plug in 1. If we plug in 1, we get 1 squared, which is 1, minus 1, which is 0. So it goes through the point 1 comma 0. And if we plug in negative 1 all squared is also 1, minus 1 is also 0. So there's those points. Let's plug in just a few more here. How about 2, negative 2, 2, negative 2, 3, and negative 3. And that should be plenty of points to get a pretty accurate graph. If you plug in 2 squared, or 2, you'll get, plugging it all in right here, okay, so plug those in and then plot these points. So we have the point 2, comma 1, 2, 3, negative 2, 1, 2, 3, and 3, comma 8, which is just underneath this parabola. It almost looks like it's touching, but it's not. So you can see these two graphs actually have the exact same shape. The only difference is that g of x is shifted. It's the same shape as f of x, but it's shifted 1 unit down. Okay, and that's actually what this -1 there does. That's going to shift it, the graph of f of x equals x squared, 1 unit down. Okay, now let's see what happens if we add a number instead of subtracting. So now let's graph h of x equals x squared plus 1 on these same axes. Okay, plugging in points there, plug in points here to make your t-chart. Okay, and then we can plot those points. So we have the point 0, 1, 2, 3, 4. That's going to be the vertex there. Then 1, 5 and -1, 5. Then 2, 8. And -2, 8. Then 3, 13. Let's see if that's even on this graph. 1, 2, 3. 8, 9, 10, 11, 12, 13, just barely. So here's the graph of h of x, which is equal to x squared plus 4. And you can see it too has the exact same shape as f of x equals x squared. The only difference is it is shifted up 4. So what I want to do here is generalize what happens when you subtract a number from x squared and when you add a number to x squared. How does that change the graph of x squared? Okay, and here it is right here. If you have f of x equals x squared plus some number, now plus some number k. If k is positive, then the graph of f of x equals x squared plus k is the same as the graph of f of x equals x squared, but it's shifted up k units. So the important part here is if k is positive, it's shifted upwards k units. If k is negative, for example, with the -1 here, that would be a negative k, then the graph is shifted downwards k units. And what is the vertex? Well, the vertex, let's see, in the original function, the vertex is 0, 0. On the h of x, the vertex is 0, 4. And on g of x, the vertex is 0, -1. So as you can see, that k is the y value of the vertex, and the x value is still 0. So the vertex is 0, k. And the axis of symmetry for all of these is the y-axis. Alright, so that's that generalized. When you add a number to x squared, that shifts the graph up and down. Next, let's graph these three functions. Again, we'll start with the basic f of x equals x squared. Now, what these graphs are going to look like, g of x and h of x, it's a little less intuitive here actually. So this t-chart will be a little bit more important for these. So we're going to plot g of x and h of x by using t-charts. Alright, this time instead of starting at 0 and going out, I'm just going to start at a negative number and then go from left to right. I think that will simplify the process a little bit. So let's start at -5. We don't have to plot every single number for both of these functions. We'll just do the ones that seem appropriate, that give us y values that at least fit on this graph. Okay, so let's plot g of x in orange, and we'll plot h of x in blue. Okay, now let's start by plugging in some values into g of x. Now if we plug in -5, we'll have -5 minus 4, that's -9, and -9 all squared is 81. So that is way off this graph, not going to fit. So let's jump down to, how about -2? Let's try plugging in that. If we plug in -2, we'd have -2 minus 4, which is -6, squared is 36, still way off the graph. Let's try 0. If I plug in 0, I get 0 minus 4, which is -4. Squared is 16. Okay, it's still off the graph, but it's at least a small enough number. Okay, so let's try 1. If I plug in 1, I'll have 1 minus 4, which is -3. -3 squared is 9. Okay, we're on the graph. So we have the point 1 comma 9. Okay, let's plug in 2. 2 minus 4 is -2, squared is 4. If we plug in 3, we get 1. If we plug in 4, 4 minus 4 is 0, 0 squared is 0. And it's starting to take a shape here. If we plug in 5, 5 minus 4 is 1, 1 squared is 1. If we plug in 6, we will get 4, and if we plug in 7, we'll get 9. Okay, so here's the graph of g of x, and you can see it also has the same shape as f of x equals x squared, but it's shifted, looks like 1, 2, 3, 4 units to the right. Which is maybe not what you expected because you have a -4. Typically minus would mean go to the left, but in this case the -4 shifted the graph of x squared 4 units to the right. Okay, now the difference between this x minus 4 all squared and this up here x squared plus 4 is that over here the plus 4 is hanging off the edge of the x squared. The plus 4, in other words, is not being squared. Down here we have x minus 4, and that's all squared. So the -4 is also part of the thing that's being squared, and that's the difference between the function going up and down or left and right. So now let's graph h of x equals x plus 2 all squared, and you can probably guess because the sign is different. We have a negative here and that shifted it right. We have a positive sign here, so my guess is that's going to shift it left 2 units. So let's see what happens. Let's start by trying to plug in -5. If we plug in -5, we'll have -5 plus 2, which is -3. Squared is 9. We can plot that. There's -5 comma 9. -4 plus 2 is -2. -2 squared is 4, so we have -4 comma 4. -3 plus 2 is -1, squared is 1. -2 plus 2 is 0, 0 squared is 0. -1 plus 2 is 1, 1 squared is 1. Plug in 0 here, we get 2 squared, that's 4. If we plug in 1, we'll get 9. If we plug in 2, we're going to get 16, which is off the graph, so we'll just go with this. So here's a rough sketch graph of h of x is equal to x plus 2 all squared. And you can see that did, in fact, shift the original graph of x squared 2 units to the left. Okay. So let's generalize based on these examples. Okay, more generally, if you have f of x equals x minus h all squared, where h is some number, Now it says x minus h, so this is a little odd because we have a minus here in the general formula. But if you have x minus a number that's and h is positive, so if h is positive, so you have, for example, something like x minus 4 all squared like we had here in orange, it's going to shift it to the right h units. If h is negative, well, if h is negative, then this would be x minus the negative number, so it would actually be x plus, you would have a plus sign there basically. Okay, I don't want to write that because that's technically wrong, but you would have a plus sign in between the x and h if h is negative. Then it shifts it to the left h units. Okay, the vertex on each of these, the only thing that changes about the vertex is the x coordinate of the vertex, not the y coordinate. The x coordinate on g of x is -2, 0, so it's equivalent to h, because in this case this is the same as x minus -2 all squared, right? So h is equal to the -2 because you have to correspond a minus to this minus in the general formula right here. So this says x minus h, so now this is written in the form x minus h, so that h would be -2 here. Anyways, it shifted. Now the vertex is -2, 0, so it looks like the vertex is h, 0. And the vertex on this one is 4, 0. And yes, h is equal to 4 on that one. So the vertex becomes h, 0 on these. Okay, that's it for the left and right shifting. Now let's combine what we've learned so far and practice this on a problem. Now we can do this one without plotting points. So what we'll do is we'll shift it using the shifting techniques we've just learned, sketch a graph, and then we'll check by checking at least 1, maybe 2 points. Okay, so this -2, because it's inside the parentheses and it's being squared, that's like these up here. That's going to correspond to left and right shifts. Now this says minus a number, so that's going to shift it to the right, okay, because h here is positive, so it shifts it to the right h units, or 2 units. Okay, so that part right there shifts the original graph of x squared to the right 2 units. And the +3, that's just hanging off the end there. The +3, because it's not part of the thing being squared, that's like the first 2 that we did. So that plus a number is actually going to shift it up so many units. So that's going to shift it up 3 units. Okay, so here's how I graph. Now, I'm going to start with y equals x squared because it's going to help me to explain how I do this. But you don't have to graph this one. I'm actually not going to fill it in. I'm just going to plot those points. That's for y equals x squared there in black. Now let's graph this function here in orange, f of x. So all these points go right 2 units, up 3 units. So I know the vertex is going to start right 2 units, up 3 units. So it's going to be at 2, 3. That'll be the vertex. Now, here's what I'm thinking. When I graph y equals x squared, if I start here at the vertex, I know that I go right 1, up 1 to get to the next point. So here I'm going to go right 1, up 1. That's equivalent to shifting that point right there. I also can, from the vertex, go left 1, up 1 to get to the next point. So here's the vertex. I'm going to go left 1, up 1. There's the next point. From the vertex, I know to get to the point 2, 4, that's that black point there. Start at the vertex, I go right 2, up 4, or I could go left 2, up 4. So over here, I'm going to go right 2, up 1, 2, 3, 4, and I'm going to go left 2, up 1, 2, 3, 4. Then I know the next point on y equals x squared is 3, 9, so that's right 3, up 9, or left 3, up 9. So I'm going to go right 1, 2, 3, up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, or left 3, up 9. And then that's plenty of points to sketch in a decent looking graph. Make sure it's curved at the bottom, it's not a V. Also at the top, it's not supposed to be vertical, these two parts. They're supposed to be slightly slanted. Okay, and there it is. There's the graph of f of x equals x minus 2 all squared plus 3. Okay, now let's check by plugging in a point. See, when I shifted it, I got that this point right here, let's check with that one, is on the graph. So let's see, what are the coordinates of that point? Looks like they're 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Looks like the coordinates of that point are 4, 7. So if I plug in 4, hopefully I get 7. 4 minus 2 is 2, 2 squared is 4, plus 3 is 7. So it looks like we did it correctly. So that's how you can graph something of this form using transformations. Okay, here's the more general explanation down here. If your parabola is of the form f of x equals x minus h all squared plus k, it has the same shape as y equals x squared. The vertex is h comma k, and the axis of symmetry is the line x equals h. But basically, this shifts it left or right h units and up or down k units depending on whether h or k are positive or negative. Okay, next we're going to add in one more piece to the puzzle, and that is what happens if the x squared has a coefficient other than 1. This one has 2, this one has a coefficient of 1/3, and this one has a coefficient of -3. So we're going to see how all of those coefficients on the x squared affect the graph of y equals x squared. So again, let's start with our basic graph of x squared. Okay, there's y equals x squared. Now let's plot g, h, and k. So we have 3 functions to plot this time. Okay, let's color code this. Let's do G in orange, we'll do H in blue, and we'll do K in pink. Okay, let's choose some X values here. And let's go from left to right. Now none of these are shifted left, right, up, or down. So we can just go with our simple x values of -3, -2, -1, 0, 1, 2, and 3. That should be enough points to plot all of these. If we need more, we'll just add in some more down here at the end. Okay, for g of x, well, from here you just plug in points, and I think it's very important that you do this by hand so that you really see and get a good understanding of how these numbers are affecting the graph of x squared by doing it by hand. If you graph them on a calculator, you're not going to understand as well. So for g of x equals 2x squared, if I plug in -3, it's -3 squared is 9 times 2 is 18. A little off the graph. If I plug in -2 squared is 4 times 2 is 8. That point we can plot. -1 squared is 1 times 2 is 2. 0 squared is 0 times 2 is 0. And these points are just going to reverse to 8 and 18. H of x equals 1/3 x squared. -3 squared is 9, and 1/3 of 9 is 3. That's a very low point there. -2 squared is 4. 4 times 1/3, that's 4/3. Or if it helps, think of it as 1 1/3 when you're graphing. Negative 1 squared times a third is positive a third. 0 squared times a third is still 0. And these are still also just going to reverse. Now in that one we may need more points actually because these y values only vary between 0 and 3. So let's plug in 4 and 5 in just for h of x. If we plug in 4, we have 4 squared is 16 divided by 3. That's 16 thirds. We need to think of that as a mixed fraction in order to graph it. So that would be, let's see, 15 thirds is 5, so that would be 5 and a third when we graph it. And the same is actually going to be true for negative 4, so that's true for positive or negative 4. And if x is positive or negative 5, we square it, we get 25 thirds. See, 24 thirds is 8, so 25 thirds would be 8 and a third. That gives us a few more points to plot. I think that should be plenty now for h. Then plugging into k, negative 3 squared is 9, times negative 3 is negative 27. Negative 2 squared is 4, times negative 3 is negative 12. Negative 1 squared is 1, times negative 3 is negative 3. 0 will give us 0, and these points are all, again, just going to reverse. Okay, so let's now sketch these graphs. So notice they all have 0, 0 for the vertex. Now there's really only a few points you can plot because on g of x, 3, 18 is off the graph. It's off these axes anyway, so, but you can get the idea from just plotting these points that it's a skinnier version of x squared. Plotting h of x, we get something like this. It's a little bit wider than the regular x squared. So it looks like if the coefficient of x squared is, when it's 2, it gets narrower, but when it's a third, it gets wider. The cutoff point here is 1, because if the coefficient was 1, you would have your regular graph y equals x squared. So if the coefficient of x squared is bigger than 1, then you get a narrower graph. In other words, it's actually stretched upwards. That's usually the way this is described. It's stretched upwards by a factor of 2. H of x is actually squished by that factor of a third, so it's wider. Now let's look at k of x. The difference here is k of x has a negative coefficient, and if you'll notice, all of these y values are negative. So that's what a negative coefficient will do. Still goes through 0, 0. Then it goes through 1, 3, and negative 1, 3. Then we go through 2, negative 12. And negative 2, negative 12. So the 3 part is making it skinny. That's what's really causing it to stretch so much. But the negative is what's causing it to open down. Okay, so we can generalize all of these findings. If you have a function, f of x equals ax squared, if a is positive, the parabola will open upwards. So these two coefficients, 2 and 1/3, are positive. So notice those parabolas open upward. If a is negative, the parabola opens downward. That's like k of x. If the absolute value of a is greater than 1, meaning a is greater than 1 in magnitude, then the graph of the parabola is narrower than the graph of y equals x squared. So we have two examples of that here. 2 is greater than 1 in absolute value, and negative 3 is greater than 1 in absolute value because the absolute value of negative 3 is positive 3, which is greater than 1. So the absolute value of the coefficient is bigger than 1, so it's narrower. And if the absolute value of the coefficient is less than 1, then the graph of the parabola is wider. That's like the g of x here with the 1/3 coefficient. Okay, so now let's put everything we've done together for one last final problem here. Let's graph using transformations. Let's graph this function, f of x equals 2 times x plus 3 all squared minus 4. Okay, the plus 3 here on the inside. The plus 3, if it's in right there next to the x and it's also being squared, that's a left and right shift. And this is where the signs are backwards. A plus shifts it left and a minus shifts it right. So because it's plus 3, it's going to go left 3 units. Then we have this minus 4 at the end. So because it's at the end of the whole thing, that will shift it up and down. Because it's minus, it's going to go down 4 units. And the only other thing we have is this coefficient here, that 2. And that's just like the coefficient that we dealt with in the previous examples. It's positive. Okay, 2 is positive, so it's going to open up, the parabola will. And it's greater than 1 in absolute value, so it's going to be narrower than y equals x squared. How much narrower? Well, by a factor of 2, or what the y values get stretched by. So we'll just plot a couple of points to make sure we get it just right on the how much narrower part. But we can plot the vertex exactly by simply shifting. The vertex goes left 3, down 4. So we go left 3, down 1, 2, 3, 4, right there. Now normally, when you graph a parabola, you go left 1, up 1 to get to the next point. But this one is stretched vertically by a factor of 2. So instead of going left 1, up 1, I'm going to go left 1, up 2. Now let's check. That's an x value of negative 2 that I'm plugging in right there. So let's find f of negative 2. And I get 2 times 1 squared, so that would be 2, minus 4 is negative 2, and that's exactly where this is, negative 2, comma negative 2. So the other point's going to mirror that. Normally on a parabola, from the vertex to get to the next point is 2, comma 4, so you go right 2, up 4. But because this is stretched by a factor of 2, I'll go right 2, up 8. Instead of right 2, up 4, we go right 2, up 8. And if you want to check that one as well, you could. We could plug in f of negative 1. That's that x value there. Hopefully we get 4. And negative 1 plus 3 is 2. 2 squared is 4. And it looks like, yes, we do get 4. So the other point just mirrors that. Okay, here's the graph of f of x. We didn't have to plot a million points to do it because we used transformations, and then I just did these couple points to check. Okay, so the vertex is at negative 3, negative 4. Okay, which is h, comma, k in these general formulas. And the axis of symmetry, let's define that because we have not labeled that in any previous examples. The axis of symmetry is a vertical line. Therefore, its equation is given by x equals a number. In this case, it's drawn at x equals negative 3. That's the axis of symmetry right there. X equals negative 3. Now, the axis of symmetry is not just negative 3. It's an equation of a line. It's x equals negative 3. Okay, so we can generalize the whole thing that we've done here. Graphs of quadratic functions. If they're written in this form, f of x equals a times x minus h all squared plus k. That's called vertex form of a parabola. Then it has vertex hk. If a is positive, greater than 0, it opens upward. If a is negative, it opens downward. There's the two differences right there. And the axis of symmetry is the line whose equation is x equals h. Okay, so that's it for graphs of quadratic functions. Actually, in section 11.6, we're going to do a little bit more with graphs of quadratic functions. So join in next time for that.